Welcome to this module. Here we want to understand the application of the operational amplifier in terms of band pass filter. So, until now what we have seen? We have seen that if you want to pass high band of frequency, we design a high pass filter. If we want to design the low band of frequency, we design a low pass filter. What about we want to pass only a certain band in your frequency range, right? Not low, not high, but within somewhere set of frequencies that only we need to pass. See, again and again I am talking about frequency, frequency, frequency. That is why at the starting of this particular filter session we talked that filters are the most important or highly used circuits in the communication systems, right. That is why we talk about frequency, frequency, frequency. So, if I want to pass a certain band of frequency, then I have to design a filter which will be my band pass filter, right. So, how to design this band pass filter, and can we design it with the help of operational amplifier? That is the idea, that is the gist of this particular module, that you have to understand, that the how to design a band pass filter. So, before we design the band pass filter with the systems that we have, with the equipment that we have here, which is our DC power supply, we have our oscilloscope, function generator, breadboard, multimeter, and of course the operation amplifier. Let us first see what exactly the band pass filter is, right. We have seen this in theory class, we are again repeating it so that you guys do not forget, right. See, the principal characteristics of a band pass filter or any filter for that matter is its ability to pass frequencies relatively unattenuated over a specific band or spread of frequencies called the pass band. What does that mean? That a pass band filter or any filter, its basic ability is to pass frequencies relatively unattenuated. That means that frequency should not be unattenuated for a specific band. It can be low pass filter, then low frequency band, high pass filter, high frequency band. That frequency that we want to pass, it should be passed without any attenuation, right. So, that is called the pass band, we already know, and attenuated the other bands of the frequency called the stop band. Okay. We know what is pass band, we know what is stop band, we also know, correct. Now, simple band pass filter, the second point, can be easily made by cascading together a single low pass filter with a single high pass filter. So easy, very easy, right. If I cascade a low pass filter with a high pass filter, I can get a band pass filter, right. Here you can see the circuit, not exactly circuit, it is a block diagram. You apply a input signal, you have a high pass filter, you have amplification, you have low pass filter, you have the output, and then you can, using this particular block, when you connect like this, you can get an active band pass filter. Why active band pass filter? Because there is a amplification involved, right. Also, when you want to design, so what we understand, when we want to design a band pass filter, we can integrate or cascade a high pass filter with the low pass filter, alright. So, the cutoff frequency, point number 3, let us see. The cutoff frequency or corner frequency of the low pass filter is higher than the cutoff frequency of the high pass filter, alright. The cutoff frequency of low pass filter is higher than the cutoff frequency of high pass filter, and the difference between the frequencies at minus 3 dB point will determine the bandwidth of the band pass filter, That means, if I draw a band pass filter, I will have something similar to this, right. So, what is this frequency Fc? This will be Fc, this will be another Fc, right. So, we are talking about these 2 points, this and this points, when we talk about this particular point, which is point number 3. What is that? It is written that the cutoff frequency of the low pass filter, right here, low pass filter, we will see is higher than the cutoff frequency of high pass filter, and the difference between frequencies, if I say this is f L and this is f H, then the difference between f H and f L, this is my band of frequencies that I want to pass, alright. So, the difference between frequencies at minus 3 dB point will determine the bandwidth. That means that if I design a filter, then if I want to know the bandwidth high pass filter, what I will do, I will design a filter like this, and I know this is high frequency, low frequency, f H minus f L will give me bandwidth, here, band of frequency, alright. So, what is written will determine bandwidth of band pass filter while attenuating any signal outside these points. Any signal outside these points means with this point and this point, no signal here can be allowed, only this particular signal between this point and this points are allowed. That means, this is a band of frequency that we can pass, alright. So, if this is the case, and if I want to design a passive band pass filter, then what can I do? If I want to design a passive band pass filter, what can I do, right? So, I have a high pass filter stage, I have a high pass filter stage, I have a low pass filter stage, I have a high pass filter stage, I have a low pass filter stage, and if I integrate high pass with low pass, if I integrate the high pass stage with low pass stage, I will get a passive band pass filter, right. Amazingly easy, is not it? Because it is so simple that by integrating the high pass filter to the low pass filter, we can get a band pass filter. Now, we all remember, right, we should all remember that in high pass filter there was capacitor at the input, and then capacitor was in series with resistor. In low pass filter, resistor and was series in capacitor, right. Output voltage across the high pass was measured across this resistor, output voltage across low pass was measured across the capacitor, right. So, if I integrate both, it becomes a band pass filter. How? So, you see this cascading storage. So, what is high pass filter? We know, right, high pass filter, if I draw the frequency, if I draw the plot is that high pass means I will have a pass from here to here. I will have a low pass filter means I will have pass from here to here, correct. So, if I join this one and I join this one, what will I have? I will have, if I join plot A of high pass filter and plot B of the low pass filter, if I join both, I will have plot which looks like this, right, which is my plot C, right. So, this is what is shown here. You see high pass A, low pass B, we integrate it, we join it, becomes C, which is band pass. This is what we are doing here, right. So, point is, for designing a passive band pass filter, we can cascade the individual low and high pass filters and produces a Q factor typical type of filter circuit which has a wide band pass, So, the cascading together of the individual low pass and high pass filter produces a low Q factor, right, type filter circuit which has a wide band pass. Cool, very easy. So, you can also design this kind of circuit, right. This is your simple passive band pass filter. Now, if there is a simple passive band pass filter, then let us do the simulation. See, if I connect it and if I do the simulation, what I get? I have the frequency on the y axis, x axis, and gain on the y axis, right, gain, frequency, right. And when I design this, I see at the output voltage a plot similar to this, which is the gain versus frequency, and I will have a band, I have a band which I am allowing to pass. I have a band which I am allowing to pass. Outside this it cannot pass, so I did here it cannot pass. There is a band at which minus 3 dB we have to calculate. So, we can have some band which is around this value, right. This you can do again with simulation, and you can find it whether it makes sense or not, right. The point is you can design a band pass filter with your passive components, and let us take an example of band pass filter. Let us take an example of band pass filter. So, you have to design a band pass filter, right, passive band pass filter with a low cutoff frequency of 1 kilohertz, with a resistor of 10 kilo ohm and high cutoff frequency of 30 kilohertz with a capacitor of 510 picofarad. This is the question given to you, and let us solve how we can design an passive band pass filter with this particular value. So, what is given? We are given 1 kilohertz. So, low cutoff frequency FL 1 kilohertz, okay, with a resistor value of 10 kilo ohm. So, let us say R1 10 kilo ohm. Higher cutoff frequency FH 30 kilohertz, capacitor C 510 picofarad, right. Now, what is the formula? F equals to 1 by 2 pi RC. That means that if I substitute the values, I will have capacitor C1 equals to 1 upon 2 pi FCR, right. I have 2 pi into FC, which is my 1 kilohertz, into my R, which is 10 kilo ohm. Then I will have value which is 15 nanofarad, approximately 15.8 nanofarad or 15 nanofarad. If I use another formula which is 1 upon 2 pi RC. So, if I want to measure the R2 would be 10 kilo ohm, correct. So, from here what we find is that we can measure the value of R1 and we can measure the value of C1 given this following units values, alright, and the value of R2 C2 required for low pass stage. See, so from here R1 and C1 required for high pass stage to give a cutoff frequency of 1 kilohertz are 10 kilo ohm and 15 nanofarad, while R2 C2 for a low pass filter is 30 kilohertz and 10 kilo ohm and 510 picofarad, right. So, these values we can calculate, and from this now we can design a passive band pass filter. We can design a passive band pass filter. Now, do not always rely on whatever I am saying, right. Always try to do your measurements by yourself. It is not that always whenever teacher gives you a solution it may be correct. Here it is okay, but I am just saying, right. You have to calculate by yourself and calculate whether the values that is there are correct or not. If not, you correct it, because it is just putting formula F equals to 1 upon 2 pi RC, 2 pi into RC, R equals to 1 upon 2 pi FC, right. Put the formula and find the values. Do not rely that okay, if there is something here 15.9 nanofarad, this is a wrong, is not like that, okay. So, try by yourself also, okay. So, now you know how to design a RC passive band pass filter, right. So, what if I have a simple active band pass filter? What if I have a simple active band pass filter, alright. So, again what I need? I will need a high pass, I will need a low pass, and I have to use active means op amp. Here I am using again a non inverting amplifier, right. So, you see you have a high pass filter at stage 1, which is here, you have low pass filter at stage 2, which is here, and then you have your inverting amplifier, non inverting amplifier here, right. We apply this input signal to the non inverting terminal of the amplifier. That means that now by cascading the high pass with low pass and integrating high pass with amplification and then connecting it to low pass, this will give us a high a simple active band pass filter. Alright. What I am saying, we have high pass filter, we have low pass filter, and we have amplifier, right, non amplifier. When we integrate it, this plus this plus this, we get an active band pass filter, right. This cascading together of individual low pass and high pass filter produces a low Q factor type filter circuit which has a wide band pass, band, right, and this is how we can create your active band pass filter, right. Here you can see we get the active band pass filter. Easy, extremely easy, right. So, this is easy, then let us see the resonant frequency. What is resonant frequency? So, here you see when you have this kind of plot, there is a FL, there is a FH, right. Frequency above this will not be passed, 3 dB not allowed to be passed, frequency below this not allowed to be passed, only this frequency will be allowed to pass, that is why it is called pass band. This is not allowed, stop band, corner frequency or FC, this is central frequency FH, right. If you consider phase, then you will have a phase shift like this, alright. You have phase shift which is shown here, right, with respect to center, with respect to FL, with respect to FH, alright. Now, the center frequency or the resonant frequency, at which the output gain is maximum can be obtained by calculating geometric mean of lower and upper cutoff frequencies. Now, we have seen this already in the lectures, but let us again look at the formula. We know that the resonant frequency or the center frequency can be obtained by calculating geometric mean of the lower and upper cutoff frequencies. That means that Fr equals to square root of Fh into Fl, right, Fh into Fl, where Fr is the resonant frequency, Fh is the upper minus 3 dB cutoff frequency, this one, Fl is lower minus 3 dB cutoff frequency, this one, Fl, right. So, now we know the formula for resonant frequency, So, what we get here is that we now know what is resonant frequency, okay. We also know what is the formula for resonant frequency, alright, correct. So, if I take an example, the calculated cutoff frequency was found to be FL equals to 1 kilohertz, FH equals to 30 kilohertz. Calculate central resonant frequency, Fr is this, right. Now, we already know the formula for Fr is square root of Fh into Fl. If I substitute the values, Fh is my 1 kilohertz, so 1000 hertz, Fh is 30 kilohertz, so 30,000 hertz, then I have my resonant frequency or central frequency as 5.477 kilohertz. So, again an example of band pass filter, you can find the solution of this kind of problems at home. It is very easy to find, is not it, very easy, extremely easy, cannot be easier than this, right. So, try to find it at home. Now, this is an exercise, again you can use a PSpice, right, and we have a non-inverting active band pass filter as shown here, right. You can see bias voltage, right. You are looking at the low pass filter, you are looking at the high pass filter, you are looking at the non-inverting amplifier here, right. And then when we use this, you will get a curve like this, a signal like this. You have to find what is Fh and what is Fl, right. What is this frequency and what is this frequency, right. This will be at minus 3 dB, minus 3 dB, alright. So, when you see this, you solve it and you will find that FH or F1 is 500 hertz, F2 is 1.5 kilohertz, or FL is 500 hertz, FH is 1.5 kilohertz, alright. So, if you do this kind of problem, you can solve it using PSpice. So, the advantage of this PSpice is you do not really require the equipment that we are showing it to you here. However, until and unless you really work on the equipment, work on the circuit, you will not get idea where the problem was, because when you start working with the circuit, you will find lot of problems that you will encounter while you design the circuit, alright. Theoretical design is one game, simulation is another game, experimental is third game, right. You have to play all the games to be successful, alright. So, do not leave anything behind, learn theory, learn simulation, learn experiments. So, coming back to the screen, this is the active band pass filter inverting configuration, right, inverting configuration. Here the formula is again the same, FC1 is nothing but FC1 is your this one. So, we have to see 1 upon 2 pi RC1, FC2 is 1 upon 2 pi RC2, right, and your voltage gain is minus R2 by R1, because this is inverting op amp, inverting op amp. So, earlier it was non inverting band pass filter, this is inverting band pass filter. It does not matter whichever you use, because the idea of using op amp is to use as an amplifier, alright. So, if you want to amplify the signal along with filtering, you can use the operational amplifier in inverting or non inverting type. This is one more example, right, this is one more example before which we will go to the actual experiment, is band pass filter. If calculate higher and lower cutoff frequencies of active band pass filter, right, as shown in figure 14. Suppose we are given this figure and we are asked to find FL or what is that, higher and cutoff frequency, okay, FL and FH. If we are asked to find, then how can we find this frequencies based on the values given in the circuit, right. So, R1 is given, C2 is given, R2 is given, C3 is given. Now, FC1 is nothing but, I have told you earlier, right, FC or FL, right, FL you can say FC1, FC2 or FL also is nothing but 1 upon 2 pi R1 C2, right. FH or FC2 1 upon 2 pi here R2 C3, R2 C3, right. So, from here if I substitute the values, C2 is what, 0.1 microfarad, R1 is what, 10 kilo ohms, I get value 159.19 hertz, alright. If I put the value here, right, R2 is what, R2 is my 1 kilo ohm, C3 is what, C3 is 0.1 microfarad, then I get value of 1.591 kilohertz. What is the gain? Gain is R2 by R1. Why minus R2 by R1? Because if you see the screen, you will find that it is an inverting amplifier, right. So, gain is minus R2 by R1, or it is minus 1 by 10, or it is 0.1, gain is 0.1. Do not write minus 0.1, okay, this is wrong, gain is 0.1, alright. So, F equals to 1 upon, so using this formula FL, FH, you get FL, you get FH. Now, see lower and higher frequency, we can also say cutoff frequency 1, cutoff frequency 2, that is why it is FC1 and FC2, right. So, do not get confused that what is FC suddenly from FL is nothing but you can also write FC1 equals to FL, FC2 equals to FH, this is also correct, alright, this is also correct. So, what we understood is that once we know the formula, which is super easy formula 1 upon 2 pi RC, right, then we can solve lot of things when you are given a circuit and you are asked to find the value of upper and lower cutoff frequency, right, which is right in front of you, right in front of you of this particular figure. From this particular figure, now you can very easily find what is lower cutoff frequency, what is higher cutoff frequency or upper cutoff frequency, and what is the gain of the amplifier, what is the gain of this amplifier. Easy, super easy, right. So, we will see. So, now I help you to understand what exactly this band pass filter is, and we have seen how you can design a passive band pass filter by using the high pass filter and low pass filter. By integrating high pass filter and low pass filter together in passive way, it becomes passive band pass filter. If you use op amp in between the high pass filter and the low pass filter, it becomes your active high pass filter, active band pass filter, right. And instead of in op amp, you can use non inverting operational amplifier, you can use the inverting operational amplifier. So, by using this non inverting and inverting operational amplifier, your formula for gain would be slightly different. Inverting amplifier, it will be minus R2 by R1 or minus RF by Rin, non inverting amplifier it will be 1 plus RF by Rin, right. Otherwise, the things remains super simple. For frequency formula, always remember it is f equals to 1 upon 2 pi RC. In case of a high pass filter and low pass filter, the high pass filter you can see the first C and first R you have to calculate. For the low pass filter, the feedback resistor and capacitor is there, that you have to calculate whatever the value is there. Once you know FH, once you know FL, if FH minus FL will give you this band, which is your bandwidth, and that is your bandwidth of your band pass filter. Now, once we know this, let us now perform the experiment, and we will continue this experiment in the next module, because now we have understood or we have refreshed the theory that we have already learned earlier, right. So, if you are every day you just spend some time, and or in a week you spend some time, apart from the understanding what are the new uploaded videos, if you go back and see the old videos, you will understand what kind of theories you have learned. And once you understand this, I do not have to speak for half an hour or 1 hour just to make you understand again the same theory that we have done. So, try to refresh your theories, right. But at the same time, I do not want to just keep on assuming that you know everything and let us start experiment directly. That is why there is a reason that we have I have told you again the details about the band pass filter. I have told you about how the passive band pass filter is, I have told you how the active band pass filter is, I have told you how you can fabricate or how you can design the active and passive band pass filter, and now in the next module we will implement it on the breadboard. Alright. So, now you know this, let us see in the next module how you can implement it, and let us get the values at the input signal and output signal, let us measure it, let us see what kind of output waveform we see, and let us comment on it. Alright. So, till then I will see you in the next module, you take care, bye.